Okay, so this is a typical example of questions under electrolysis. So we're going to look at this as a representative of different pools of questions that we may be having. A current of 2 ampere flows for 2 hours, 40 minutes, 55 seconds through a solution of copper sulfate using platinum electrode. A. Calculate the quantity of electricity that passed through the electrolytes. B. How many Faradays were consumed? C. What mass of copper is deposited at the, what do you expect this to be? Copper is deposited. Where is copper usually deposited? I purposely left this empty so that we can feel it. I want you to do that. What volume of oxygen gas will be liberated at the, one of these is the cathode, the other one is the anode. So I want us to fill it up. What happens to the copper sulfate at the end of the electrolysis? Of course, copper is a cation and therefore it has to be what? Migrated. It has to migrate to the cathode and therefore get deposited at the cathode. And of course, oxygen is always getting from hydroxyl ion, OH minus. Whenever you have hydroxyl ion migrating, you know it's an anion, and it has to migrate to the anode. Whenever it is preferentially discharged, two things will always be produced: water and then oxygen. So oxygen will be liberated at the anode. And then the last question. Now, without wasting any of our time, calculate the quantity of what? Of electricity that passed through the electrolytes. From the beginning of the class, I showed you that quantity, which has a unit of what? Coulomb, is always current and time. Current and what? Time. It therefore means the quantity we are looking for, the current is 2 ampere. Alright, before we actually solve this, we've got to write out the variable or the parameters. In this case, our current is 2 ampere. Our time should always be in seconds. In fact, this is question that should teach us how to approximate all our time in seconds. We have 2 hours. To get your 2 hours to minutes, you multiply it by 60, and then to convert it to seconds by another 60. All right, plus this is already in minutes. To go down below to seconds is going to be times 60, then plus the other one that is already in seconds plus 55 seconds. If you do that properly in theory questions, this step would always fetch you its own mark. So 2 times 3,600, that is 7,200. 7,200 plus 40 times 60, 2,400 plus 55. It therefore means your time is equal to 7,200, and that is 9,655 seconds. 9,655 seconds. I purposely wrote it in this way so that in exam hall you are going to try to be as less ambiguous as anything. You have to be specific. If this is looking like 5 examiners, if I stop here, some examiners may consider this as 5 and as not the units. Of course, the unit should be in seconds, but to be much more precise, you can have this. So this is our time. It therefore means that the quantity of electricity that passed through the electrolyte is going to be equal to the formula IT, which means your quantity is equal to 2 times 96 5. And therefore your quantity is equal to 19310 coulomb. Right? So the quantity of electricity that passed through this electrolyte is 19,310 coulomb. 19,310 coulomb. So we are done with the first question. It has to be done stepwisely. So the second question B, how many Faradays were consumed for this reaction? All right, electrolytic reaction. How many Faradays were consumed? Remember, I told you from part of the question that 1 Faraday is usually equal to 96,500 coulomb per mole. But in this case, the quantity of electricity that passes through, for every 1 Faraday, you have to get this amount of quantity of electricity. But in this case, we have 19,310 coulomb of electricity that passes through the electrolyte. It therefore means X Faraday will give you 19310 coulomb. Mathematically, you do what? You cross multiply. 1 Faraday is giving you this X Faraday because they're asking us how many Faraday or Faradays were consumed. 1 Faraday will always give you this. Of course, we know the quantity that passed through. So how many Faradays will be consumed? X. Right? So it means that mathematically X times 96,500 will be equals to 1 times 19310. So your X is equal to 19310 divided by 96,500 Faraday. All right, if you do that properly, all right, divided by 96,500. So what you're gonna get is 0.2 Faradays. So the number of Faraday that were consumed is 0.2. A Faraday divided by 5 is actually, because this guy is actually going to give you, this guy divided by 5 will always give you this. All right. So it means 0.2 Faraday is actually consumed. So the third question, what mass of copper is deposited at the cathode? If it were to be a question that requires answer, just the final answer, you can then introduce the almighty formula that says that M is equal to Mr. IT all over CF. Remember, mass M. The relative molecular mass of copper is 64. Current and time, we've done that. The current is 2. The time is 9655. The charge for copper 2 ion is 2. And Faraday's constant is 96,500. So the mass is going to give you 64 times 2 times 9655, 1,235,840 divided by 193,000, I suppose. 2 times 96,500. So 193,000. So your mass would be divided by 193,000, 6.4 grams. That is if and only if you were not asked about, it's not a theoretical question. That's when you go straight. You do it immediately so that you can easily pick or give your answer. But if it is a question that requires you to break down the steps, you can't go directly. Rather, you go stepwisely. Then how do you go stepwisely? You're asked to calculate the mass of the copper that was discharged. From Faraday's second law, we said that the amount, that is invariably the mass of the substance that is discharged, is inversely proportional to the what? To the charge. All right? N is inversely proportional to the charge. Are we there? So it therefore means that this number amount, which is also equals to N is equal to what? K over C. All right? This is amount, is also mass over molar mass. All right? So it simply means that the amount that we are looking for, the mass, we are interested in the charges that the ion carries. Because according to Faraday's second law, the amount is usually related to the charges on the ions. For instance, if the ion is 1, it will require 1 Faraday, all right, to discharge a mole. That's why we say coulomb per mole. 96,500 coulomb will be required to discharge 1 mole if the charge is 1. If it is 2, then it has to be multiplied by 2. In this case, copper is always 2 plus. So it therefore means 2 Faradays will be equal, or you could be equated to the molecular mass of what? Of copper. In this case, it is 64 gram. That's the standard. Because copper is 2 plus, 2 Faraday will give you 64 gram. If it were to be silver is 1 plus. It means 1 Faraday will give you 108 gram. If it were to be sodium is 1 plus. 1 Faraday will be equal to 23 gram. Aluminium, 1 Faraday equals to 27 gram, and so on and so forth. But because it is copper is 2 plus. If it is iron 3 Faraday will give you 56 gram, or as the case may be. Right? As the mass, the relative atomic mass or molecular mass of iron is. But because this is what? Copper, we are going to. So in this case, 2 Faraday will give you 64 gram. And then we are interested in what? In the amount that we are going to get, the mass that's going to be deposited at the cathode. Remember, during the electrolysis, how many Faraday was required? 0.2 Faraday was what passed through. So what will be the mass that was discharged? Simple proportionality equation. So you do the same thing, right? So that will be X, or before that, 2 Faraday is equal to 2 times 96,500. That is, if you like, 64 gram. 0.2 times 96,500 x gram. So you cross multiply. When you do that, you have 2x times 96,500 equals to 0.2 times 96,500 times 64. Mathematically, this can cancel out. Of course, it can cancel out since they are of the same signs and the same magnitude, so they can cancel out. So it means 2x will be equal to 0.2 times 64. X is equal to 0.2, are we there, times 64 all over 2. All right, so invariably your X will be equals to 0.2 divided by 2 is 0.1 times 64, 6.4 gram. In chemistry, we are interested in units. Unit also carries marks. The significance of this is that in our modern day, usual day life, if I tell you I'm going to give you, if you answer this question, I'm going to give you 1,000. I'm going to give you 1,000. As smart students, you should be able to ask me before you embark on the journey, sir, 1,000 watts. Is it 1,000 slaps? Is it 1,000 blows? Is it 1,000 likes? And so on and so forth. So I've got to specify, give you the units. $1,000, 1,000 pounds, 1,000 naira. So this is one of the reasons why you've got to specify the units. Practically, this is the step to follow. You first of all introduce the number of Faraday that is required, to discharge that element, depending on the charge. For copper, it is 2. You equate it to the atomic mass or molecular mass of the substance in question, and then you get the number of Faraday that is actually used during that particular electrolysis and try to use it to get the mass of the element that was eventually discharged. So we are done with question C. We're done with question C. Swiftly moving on to D. What volume of oxygen gas will be liberated at the anode? What volume of oxygen gas